This presentation is a seminar on the paper titled Transformers are inherently succinct. The primary focus of this session will be on examining the key differences between transformers and RNN architectures. Before diving into details, it is necessary to define two key concepts: expressivity and succinctness. Expressivity refers to the range of languages or patterns a system can recognize. For example, the ability to identify a valid email address. Succinctness, on the other hand, measures how compactly a system can describe the language. This relates to the size, how many states a machine requires, or how large a transformer must be to perform a specific task. The main contribution of this research is the proposal of succinctness as a true measure of a model power. In practical applications, models run on finite machines with limited memory and precision. Therefore, the ability to represent complex patterns using minimal parameters, its succinctness, is what truly matters for performance. To understand these models, the focus is placed on regular languages. A language is a set of words made from an alphabet, and regular languages follow specific structural patterns. For example, an email address follows a strict structure with a sender name and a domain. These languages are traditionally recognized by finite automata. A finite automata is a state machine that reads one symbol at a time and moves between states. If it ends in an accepting state after reading a word, that word is a part of the language. The diagram shown here illustrates an FA. The next topic is star-free languages. These are a subset of regular languages that do not use clean star, instead of relying on operations like union, concatenations, and complement. While many patterns can be described without the star, some cannot. A notable example is parity, which checks if a string has an even number of specific symbols. Parity is not a star-free language. This leads to a known limitation. Fixed precision transformers are restricted to star-free languages, meaning they theoretically cannot recognize parity. However, expressivity in formal language theory is only part of the story. Even within the same language class, the size of the description, the succinctness, can vary significantly between different models. To analyze this, BRASP, a Boolean sequence processing program, is utilized. BRASP uses Boolean predicates for each token position and updates them using simple rules. It includes position-wise operations and, more importantly, attention operations that can attend to a previous index satisfying a certain condition. BRASP allows for a construction of complex verifiers, such as n-bit counters. By finding the nearest previous sharp symbol, BRASP can verify if a counter increases by 1 at each block. Interestingly, an n-size BRASP program can verify a counter as large as n bits, where m equals 2 to the power of n. Furthermore, by applying attention operations, it is possible to retrieve only the required bits among the bits in a row. This is then bridged to unique hard attention transformers, or UHAT. Unlike standard attention, UHAT selects exactly one position with a maximum score. It can be shown that any BRASP program can be translated into a UHAT in polynomial time easily. This means an n-size UHAT can verify a counter that recognizes the words with length up to the power of n. A comparison of the size required to recognize these massive patterns reveals significant differences. To recognize a word of double exponential length, a finite automata would require a state space that is also double exponentially large. But on RNN, while acting as a compressed FA, would still require an exponentially large size. However, a UHAT can achieve this same task with a size of only n. This leads to core conclusion of the research. UHAT, and by extension transformers, are inherently succinct. They are exponentially more succinct than RNNs, and doubly exponentially more succinct than finite automata when recognizing complex patterns. In conclusion, the power of transformers stems not from recognizing a broader class of languages in a theoretical sense, but from their inherent succinctness. They represent and verify incredibly complex patterns using fewer parameters and resources. Thank you for attention.